Hi, welcome everyone. This is the beginning of the Understanding Deep Learning book, brand new book. So excited to be reading this. Uh, Glad people had a chance to meet some of the other people here. We're now going to talk about the content of the first two chapters. So for any of you who have ever built a model, done linear regression, hopefully this part will be fairly familiar to you. Okay, so chapter one is just an introduction and kind of an overview of the way the book's going to go. Okay, so the authors, I think different people might give slightly different answers, but the author says that machine learning is a subset of artificial intelligence. Artificial intelligence is bigger than machine learning, and deep neural networks is a subset of machine learning. Not all of machine learning uses neural networks or deep learning. So in everyday life today, you are probably encountering deep learning models. There's speech recognition on like Alexa or Siri or whatever. There's translation, computer vision models all over the place. Um, and so in this book, the goal isn't to teach you coding. The goal isn't to teach you a lot of the hands-on stuff, but rather to get at the concepts. And so that's what we're going to try to do is as Ryan said, we're going to recap the content each week of the chapters. We're not going to be like teaching it from scratch, but we'll recap it. And then we'll use the problems as an opportunity to really explore like what are the implications? What does this mean? And that's the way I really see things. So again, ideally, in future weeks, if you can try to read the chapters and then look at the problems and see which ones are difficult or which ones are there things that you don't understand. And that's what we as a group can talk about. So the author says there's three main areas covered. There's going to be supervised learning, unsupervised learning, and reinforcement learning. And then a little bit here, and then ultimately, as we go through the book, going to go into more detail. So supervised learning, right? This is a model that maps input data to an output prediction. He goes and says like, yeah, you can have a regression problem where you're predicting a continuous number, or you can have classification, that's categories. So here's a picture. Is it a dog or is it a cat? That would be binary classification. In theory, the inputs could be many dimensional, and even the outputs can be. A lot of simple models we talk about, it's like ImageNet, there's 1,000 different classes and there's only one answer. Each picture is either a dog, rose, whatever. But there are other kinds of problems where the output is actually not just one dimensional. And so then again, a little more detail here. He talks about, hey, tabular data, maybe you have 10, 100 columns, it's relatively small. A 72 by 72 pixel color image has 72 times 72 times 3 floating point inputs. And so that's whatever that is, that's like thousands of inputs. And it only gets bigger than that. Audio, right, it's often sampled at um, I mean, at least like 20,000, oftentimes 44,000, whatever, samples per second. So you're talking about, a lot of data. So then in supervised learning, you have to have labeled data in your training set. Okay. So your training set has your inputs and it has the ground truth answers, what we call your labels for what the answer is supposed to be. And we're not going to get into the details yet, but in a deep neural network, there are different architectures. So there are ones that can have just very fixed inputs. There are ones that can have variable length inputs. There's ones with simple single outputs. We're going to see some variation there. Okay. And then there's some examples here when he talks about outputs. Um, Semantic segmentation of an image is going to have an output for every single pixel. That's a lot of outputs. Okay. Monocular depth estimation is you get a picture and you say, how far away are the things that we see in here? So there's a person, they're very close to you. There's a tree that's farther away. There's a mountain that's in the background that's very far away. You're still actually giving one answer per pixel, but it's a very different kind of answer than just segmenting the image into what are the different, objects in there. so on and so forth. So that covers just a very, very quick recap of supervised learning, where again, we've got training data with labels, and we're going to train the model to see the input and to predict the labels. The author talks about unsupervised learning. This is probably going to be a slightly different discussion of unsupervised learning than you would see most places, okay? Because this is really focused towards deep learning. So in this case, he says the models are constructed with input data without labels, and we're really going to focus in this book on generative models. So generating images, for example. And so there's 4 chapters that cover different things: GANs, variational autoencoders, normalizing flows, diffusion models. And so it's important to understand this idea of latent variables. So if there is some underlying process, you can have a lower dimensional space in which you have key things that are driving things, and then the rest is just sort of like the finer details. So if you're classifying animals, you know, a latent variable might be how many legs do they have? Lots of animals have 2 legs, 4 legs. There's other ones that have different numbers, 6, 8, whatever. So if you're just looking at a picture, you're just seeing a whole bunch of pixels, but like how many legs would be potentially a very useful latent variable. Yeah. We're not saying it's easy to figure out the latent variables just from looking at a picture, but we're saying that it would be a very useful variable if you had access to it. And then he makes a connection between supervised and unsupervised learning, saying that actually, if you did something unsupervised and you had really good latents, then that could be actually very useful for other kinds of problems. It could actually help you in your supervised learning problems. A little bit of talk about RL. We'll get into it, and the book's not going to go super deep into RL, but you know, the idea is you have an agent, and it's an environment. You have typically refer to it as time steps. And so at each time step, you choose an action, and you may or may not get a reward, but the reward is just a single valued number. So it could be 0, it could be 1, it could be 10. And it's very easy to figure out, how can I maximize my reward in the very next time step? It is not easy to say, how do I maximize the reward on average over the long haul? So that's the 3: supervised, unsupervised, reinforcement learning. Talks about ethics. This is not going to be a book on ethics, but you know, it is an important topic. And so a few things that you can read about, right? Bias and fairness, explainability, the weaponization of AI. I think concentration of power is a problem with lots of things, and AI can just contribute to that already existing phenomenon. Existential risk is an interesting conversation. Some people have very strong opinions at both ends of the spectrum, whether there is any or there isn't any. And I do think it's important to note that those are sort of like biggies, but there's just plenty of things like people can, you know, do disinformation. If you have ChatGPT, it's a lot easier for you to like write plausible sounding things that, you know, aren't true. People can commit fraud. You can use, you know, these things to convince someone that it's your friend Ryan calling, but it's not actually your friend Ryan. They've just faked it. All sorts of things like that. So I think it is important that we as the people in the industry, you know, notice this. So in terms of the book, chapter 2 through 9, we're going to go through details and learn more of the mechanics about the different components. So ultimately, we'll talk about loss functions and, you know, gradient descent, things like that. We'll cover some of the different architectures. Then there'll be chapters on unsupervised learning and those 4 different kinds of models, a chapter on RL. And then there are going to be some open questions. To this day, deep learning works really well. And in fact, most practitioners that I know say that it works better than anybody can explain why it works so great. So, so that's going to be the book. And we've kind of talked about that in this book, each chapter, there's going to be the main body. So I'm talking about chapter 1 right now. The other chapters all sort of have a history section that's in the notes. I'm not planning on covering the history section. I find those sections very interesting, but not planning on covering it here. And then, like Ryan said, we'll probably try to allocate about half the time for problems. So moving on quickly here, just because we took some time for the icebreaker, so I'm going a little faster. An example of supervised learning, okay? So you're going to take your inputs and you're going to output a prediction. In the example they give here, they're really talking about just a single number as an input and a single number as an output, okay? But in more complex examples, you're going to have multiple numbers that you take as inputs. And typically what we do is we lump them together. So if you have 10 numbers as inputs, we will refer to them as a vector of length 10, a 10-dimensional input. And then we can just call that whole vector of length 10 x. The example that is given here is just a single number x. So in this case, x could be 1, it could be 10, it could be 4.2. Okay, it's not anything more complex than that. So if you look at the equations, basically we're saying we have parameters. Typically, you'll see people either use the Greek letter phi, which this author is using, or the Greek letter theta. And again, if you have only one parameter, fine. But if you have two parameters, we're still talking about phi without any subscripts as all of them. And if you hear about like llama 7 billion, it means that it has 7 billion parameters, and there's just phi sub 0, phi sub 1, all the way up through phi sub 7 billion. Okay. So because of your model architecture, these parameters are defining a particular family of functions. So in the case of linear regression, two numbers will define any line. Okay. Basically, if you know the slope and you know the intercept, then that will uniquely define a line. So if you kind of just looking at me on the screen, this would be a line sort of like a slope of 1. If you have a slope of 2, it means it's more vertical. If you slope of 1/2, it means it's more horizontal. And then if I increase the intercept, that means that the line is moving up. If I decrease the intersection, the line is moving down, but the slope is staying the same. So two parameters can define any line in the plane. And so that's the example they give where they say y equals phi sub 0 plus phi sub 1 times x. And so from algebra, from linear algebra, basically phi sub 1, the number that multiplies by x, is going to be the slope of your line, how steep it is. And phi sub 0 is going to define how high or low it is, the y-intercept. We are going to define a loss function. And so the key thing to understand here is that the loss function is the thing that's defining your goal. So in machine learning, we say we want the loss function to be as small as possible. Okay. And so we are going to try to minimize it. And then this expression here, argmin, blah, 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 that just means if you looked at all the different possible values of phi, which set of phi's are going to give you the smallest value for your loss function. Okay. Typically speaking, you can't just exhaustively explore every single possible value of phi 0 and phi 1, right? I mean, there's on the real number line, there's infinitely many phi 0s and there's another infinitely many phi 1s. You can't do every combination. So we'll need some kind of tricks. We can talk about very, very simple problems have a closed form solution. And in general, what we're going to end up doing is we're going to randomly initialize, and then we're going, what you can do for a very simple problem is you can actually just try a few values of your parameters, and you can actually create a picture of it. And so if the picture of it looks, say, like kind of like a bowl, then the idea is you're trying to walk downhill down to get to the bottom of the bowl. Okay. Now, on a high dimensional problem, you can't actually just sit there and easily visualize what the loss function is for all these different parameters. Like I said, for llama 7 billion, how are you going to visualize what changing all 7 billion of those different parameters looks like? But conceptually, that's what we're doing, and we'll get into that with gradient descent. I put a link in here, by the way. I'll post on GitHub the the link to the notes that I'm sharing on my screen. So there's a website, lostlandscape.com, and it's kind of fun to check it out. There's a paper that's associated with this, but basically they have some pictures that they've done that are of what the loss function looks like when you have like different parameters and stuff. And so they have some pretty gnarly looking pictures. This thing here you can see is, again, it's bowl shaped, but it's kind of like this, I don't know, um, this hole down in the middle. And you can see in some places things look smoother, and in other places you have these weird, spiky, very irregular surfaces and whatnot. Kind of fun to look at. All right, so kind of wrapping up here, not covering everything in the chapter again. When you test the model, you're going to test it out on held out data. And ideally, what you want is something that's going to generalize. Well, what exactly does that mean? So the model, because you trained it on a set of data, is pretty much should always do well on that set of data. Okay. If your model's underfit, it might mean that it doesn't have the ability to sort of follow the whole data distribution. So for linear regression, if you have something that's like, I don't know, height of people or whatever, and it's got a curve shape, well, linear regression can only fit a line. So even though you might fit a certain subset of the data pretty well, when you get to the ends and the data curves, the line's not going to do very well. That's underfit. And then overfit's sort of the opposite problem, where you're overly focusing on the data that you have, and basically there may be noise in the data, and if you treat all of that as the absolute truth, then you tend to get a model that too closely follows your data and doesn't work in the general case. Again, we'll talk more about that. All right, I went a little bit faster than I was hoping to, but any questions just about the basics in terms of the book and the overall supervised learning setup? All right, so then 3 problems here. We're a little bit over time.
Sorry, I had one question about
Please.
the second chapter. So, well, like he talks about the difference between discriminative and generative models, and it wasn't clear to me, like, he was giving this example. I have to pull it up for, I guess it was for a car, where he was saying that, like, in case of a generative model, you could be more descriptive. I didn't quite get it. The way I was trying to think about it is like, okay, if I have to do a regular or discriminative model, I could have some training data from which I can get the features and then map them to the output. But in the other case, when I'm doing the inverse, like starting from the output, I guess, like I can extract or think about whatever features I want. And that's why it's better, but it wasn't quite clear to me, and I've not looked at this before. So if you could shed some light on that, that would be great.
Yeah, that's a great question. So let me just give you like a super simple example, okay? So a discriminative model could be one where you get pictures, and the model says, is it a cat or a dog? Okay, so anytime you're classifying whatever fancy word for that would be discriminating. Okay, you're discriminating between cats and dogs. So they call that a discriminative model. The opposite of that would be, I tell you either the word cat or the word dog, and you produce a picture. That would be a generative model. Okay. Now, I'm not saying that this covers all of the math and all of the whatever, but like, at least from the basics, that's the difference between a discriminative and a generative model. And you could split hairs. I'm not going to say I'm the expert on like the formal right way to define it. Okay. But ultimately you run into some slightly different phenomena in terms of how things work. So when we think of a discriminative model, if you think just in terms of 2D, you've got some points, and maybe what you're trying to do is you're just trying to draw a line and say, all the dogs are on this side of my line and all the cats are on that side of the line. And And conceptually, you can think of discriminative models as doing that. They're always just trying to find a way to divide your data set. Fundamentally, generation doesn't work that way, which is, if I remember right, that's what the author was getting at. But either way, fundamentally, you do need to understand what makes a dog and what makes a cat different from a dog to do either of those things. Because if I say the word cat and you output a picture of a German Shepherd, you're not doing a very good job. So either way, you have to fundamentally understand what makes something a dog or what makes it a cat. But the math and the whatever are a little bit different. So I don't know if that was a great answer. Did that help?
I think I get like qualitatively, but based on what he is saying in the book, I think this is like page 23, where he says like the discriminative model is y equals f of x comma phi, and the generative is x equals g of y comma phi. So this is towards the end of the chapter.
Yeah, I think it's in the notes
And
actually, right?
right, yeah, exactly,
Mhm.
right here. So yeah, and so it's like this part where, you know, he says that there's an advantage. That's the part that I was like trying to wrap my head around. And he says like generative model, the last line in the page, yeah, have the advantage that we can build in prior knowledge about how the data were created, for example, to predict the 3D position and orientation
Mhm.
of a car. Yeah, you could build the knowledge about car shape and so on, right? So I think that's the part that I wasn't quite clear on. And I believe William has his hand up, so.
Yeah,
Yeah,
could
so
I? Oh,
yeah, did you want to offer something on this or a different question?
no, something on this.
Yeah, sure. Go for it.
And I'm not sure if I'm conflating terms, but I didn't read through that part of the chapter, so I don't want to try to study that this second. But my understanding, like in the classification example, if you're classifying dogs and cats, if you model those features with a Gaussian distribution, and then define a decision boundary based on, like the midpoint of those two distributions, then that would be an example of a generative model because you're modeling the data with the distribution. Whereas if you were going to use something like a support vector machine, then the decision boundary is really just based on uh, points in the feature space that you know uh, maximize the separation between those two classes, but that's not based on any notion of a distribution for the features associated with the two classes. So I've always thought of discriminative and generative, the difference between those two types of approaches as a generative model is one where you have some information about the distribution, what you think the distribution is for those classes, and you're basing your decision boundary and therefore your classification on that information. In other words, you're taking those features and you're fitting a distribution to it. So there's, Gaussian discriminant analysis does that. Other types of classification problems or algorithms rather don't attempt to fit a distribution to the data. They arrive at a decision boundary by some other means. So that was just, I don't know how. That's just how I've always thought about it. I don't know where I just over the last few years reading material, that's how the conclusion I came to about one way to describe those things, those two different.
Yeah. So again, I'm gonna say I may not have sort of the perfect rigorous formal definition, but I think what you need to understand in what I read from the part that I just highlighted, what the author's saying here, okay, what you really kind of need to understand is your notion of where your data comes from in the wild. Okay,
Mhm.
there is no in the wild thing that says dog. There is, in fact, in the wild, actual dogs. Okay, we have made a concept which is these are dogs, and these are not dogs. These are wolves. These are not dogs, these are cats. Okay. So when you think about it that way, for me, like again, I'm doing a little bit of hand waving here. It is natural to think about the distribution of actual dogs as being data, and the word dog being a label and the word cat being a label. I think if you get really, really philosophical, I'm going to have a hard time justifying which one is which, okay? But I think that just because dogs actually naturally occur in the wild, that becomes the data, and then the Ys are your labels. So in a discriminative process, what we're saying is we take data that naturally occurs and we're labeling it. In a generative model, we're going in the reverse direction. We're starting with this label, and we're generating things that look like they could be from the wild. And what I'm reading from this sentence here, which I don't know if this is the most important thing, but where he says, you know, there's an advantage that we could build in prior knowledge. You could actually say, I want a car that is facing towards me. I want a side view of a car. I want a car that's a station wagon, whatever. And you could even generate like synthetic examples and things like that. And that's something that is sort of easier to do when you're doing it in that direction. But that's kind of my best shot at interpreting this statement here.
I see. Okay. I think I'm also going to read a little bit more and try to expand my knowledge. But thank you both for your answer.
Yeah, and we're definitely going to get into this. We're not going to get into it right away because generative models he doesn't talk about until like chapter 15 or whatever. But when we do get into it, I think there'll be a much clearer intuition in terms of this idea that, like, yeah, we want to generate pictures of dogs. You can't just say do it. Ultimately, you have to build something that's going to understand what is a dog. And there was that statement about the connection between supervised and unsupervised learning. Ultimately, if you could do a perfect job of generating dogs, then you have to also be able to be discriminative. Okay. Mm-hmm. And you could argue if you had a perfect discriminator, to a certain extent, that would help you generate. It's not a generative process itself, but if you had an absolutely perfect discriminator, you could just like, it would be horribly inefficient, but you could just generate random images. And if the discriminator says that's not a dog, then you throw it away and you generate another one.
I see. Makes sense.
It'd be horribly inefficient, but it would technically work.
Yeah.
The problem is that we don't have perfect, and so we're kind of looking at different things.
Thank you.
Thanks for the question. Okay. So the author has these first two problems that he doesn't provide answers to, and then the third one that he does. And so the first one is calculate the formulas for the slopes of the loss function with respect to the first parameter, and the partial derivative, the loss function with respect to the second parameter. If you guys don't know multivariate calculus, if you don't know calculus, then you're not going to follow the math. But the idea basically is when you want the partial derivative with respect to the first parameter, phi 0, you hold all the other values constant. You hold phi 1 constant, you hold x constant, you hold y constant, everything else. And so you just treat them as if they were just numbers. You can pretend they're all ones, they're all twos, whatever. But you're still going to get some function that varies depending on this particular variable. So I took a stab at it. I don't know if I did this right. I was doing this last night. But you can see the loss function is the squared loss. So it's y minus our prediction. Our prediction is phi 0 plus phi 1 times x. So when y minus that, you got this. I square it, I expand it out, try and simplify. And then basically from this equation, if I want to know the derivative with respect to phi 0, anything that doesn't contain phi 0 is just a constant. Okay, it doesn't matter if it's 2 or if it's 2x or if it's whatever. The slope of a constant is 0. It's a horizontal line. So in this case, if you're asking what varies the slope of this loss function when you change phi 0, the parts that don't, so then basically like this is like the interesting part. Okay, and what is the slope with respect to phi 1, right? Then like this is the interesting part. And so we have two equations and two variables, and the second question said, could you solve for it? So yes, if we set the derivatives to 0, then we have two equations, two variables, and we can kind of solve that.
Can I have a question here?
Please.
But is it like the full equation, because this loss function is a sum of errors, of square errors, and here we only.
Yeah, exactly. I was trying to think about how to say this and how to do this. So in fact, if you have only one example data point, then you just have one x, one y. If you have two of them, then you have two of these. And I don't want to like lose people, but so with these two variables, if you have three, you can actually have an overdetermined system. But I think what the author's trying to get at here isn't how do I want to say this? What he's really talking about is the loss function, okay? And when you have a minimum, the slope is 0. And so he's really just trying to say, can you find a place where the derivative is 0, not necessarily talking about uniqueness or anything like that. So honestly, I wasn't 100% sure how to tackle these problems, but I was trying to keep it a little bit simpler in concept.
Actually, it is a paraboloid, many dimensional, but paraboloid. So there is a solution and it is unique. As somebody who did a lot of took a lot of derivations, I can tell you that it would be better to differentiate it without spreading out as a square. Yeah.
I could have used the chain rule. Yeah. All right.
Yeah, chain rule.
The one I wanted to talk about.
I would like to remind you that it is also you did it for x and y, but in reality, this axis and y is actually a series of equations for each x and each y. So usually we don't have overdetermination if we have enough records.
Yep. All right. Thank you. So this actually ties into the earlier question, this problem number 3. So I paraphrased, I shorten it. It says, consider reformulating linear regression as a generative model. So instead of y equals a function of x and some parameters, now x equals a function g of y and some parameters. So will this model make the same predictions as the discriminative version if you gave it the same exact training set? So again, I think this is a good question that gets at the core of, do you understand that if you go in the one direction and you say y equals some function of x and you fit something, versus if you go in the other direction, it's a mapping either way, right? It's a mapping between y and x either way. Are you going to get the exact same answer if you go in the opposite direction and you say x is a function of y? Now, in this case, these are all numbers, so it's not like my example of cat, dog. A binary category is not differentiable, okay? But in this case, imagine it's just like height is a function of age or something like that, right? So you can go in either direction. So I don't know if anybody took a look at this, but if I go to
I did
the author's website, all right. So Maya, what were your thoughts on the question about if you go, oh, I know I have it. If you go in the two different directions.
I don't have a thoughts, I have a picture. I mean, I have a picture and my thoughts. So it means that we find linear regression with respect for y, which is equal to some kind of linear function of x, and that we solve it for x when it is some kind of linear function of y. And we minimize, well, in original way, we minimize y values, and in reversed way, we minimize x values. So it will be a bit different.
Yep. Yeah. So the author answers it two ways. First, he says, here's this equation, and I can show you that the equation is not going to be the same if you go in the opposite direction. Okay. So that's a sort of formulaic mathematical answer. the more geometric intuition, he says, is if you have these 3 points, okay, I'm going to make this bigger. If you have these 3 points, when we solve it the forward direction, and bear with me one sec. Then what we're minimizing when we do a regular linear regression is we're minimizing the squares of these distances. Okay, and this one's obviously very small, these vertical distances. If you reverse the problem, if you reverse the problem, then what we're doing now is we're minimizing these horizontal distances. And you could, just by luck, happen to get the same line that would minimize both. But hopefully there's an intuition that you're not, definitely not guaranteed to get the same line if you're minimizing those 3 vertical things versus minimizing the the 3 horizontal ones. So if you look at the 2 pictures that he provides, the lines are slightly different. If you can kind of see the difference, this line on the right is a little bit steeper, this line on the left is a little flatter. And for sure, what I can tell is that this line on the right isn't very close to the left point, and it's quite close over here. But I mean, I had to kind of squint in order to really see his example. I have an example that's much more dramatic. If you guys are okay staying over time, again, even a little bit more, using my super fancy tool here. So if I start with 2 points like this, then I can fit it with a line. And obviously 2 points define a line, so the best fit line is just going to be perfect line that goes through both of them. Okay. My pathological example is if I add another point, and this point is making a right triangle. This is my 3rd point. So now it's going to be very difficult to fit a line to 3 points that are so not on a line here or whatever. But what I will tell you just intuitively is if you try to minimize the vertical distance like you do in a normal linear regression, these 2 points, there's no way you can ever get them both close to 0. Because if the line's close to this one, it has to be farther from the bottom one. And if it's close to the bottom one, it has to be farther from the top one. So the best you can do is actually by crossing here right through the middle of the 2 of them. And then you can nail that one perfectly. So the line that you're going to get for this one actually is going to look like this. It's going to go through the halfway point over here. And if you did the reverse problem, then you're gonna end up having a problem where we're splitting the horizontal distance because these 2 points have the exact same y value. The best you can do is split them halfway point. So for this one, the best possible line you can do is going to look like this, where it goes. I didn't draw it very well, but the halfway point here. So the forward regression on these 3 very bad points is going to give you the blue line. The reverse direction is going to give you the green line. So that's a much more dramatic example. I hope that helps. So the main takeaway from this, though, is that even though you're using the same data set, if you're using a particular technique, you're not going to get the same exact answer. If you had an infinite data set of all dogs and all cats, all possible dogs and cats, then if you had the optimal solution to either one of them, it's going to be identical. But for a finite set of data, and especially data that has errors in measurement and whatnot, that's not. And so I think the main takeaway from this is that forward processes and reverse processes are not automatically identical when you're dealing with real world problems. All right, so that's what we got for today. Apologize for going over time. Any other questions? Okay, great. So the plan is next week, we're going to look at chapter 3. The week after that, chapter 4, and probably we're going to do a paper talk the week after that. So just in terms of pacing. Again, please try to read chapter 3 before next week and take a look at the problems. There are, if I remember right, 18 problems. And again, they get at some of them are like simple questions like how many blah, blah, blah. But what it's kind of getting at is some of these more concepts in terms of like, as you change the number of parameters, how does that number of sections grow? And it grows very rapidly. And so that's the concept that's trying to be taught there. All right, Ryan, I think we can stop the recording here.